All right. Two things. I probably should have wrote it down, but I forgot. One is, again, office hours are in person now. So just double check with the website. I don't think any times have changed at this point, but the rooms are posted. They're all in Haas. And then two, I also haven't updated this yet, but instead of making homework due at noon, we're planning to make it due at 3, which is a little later, but still gives us some time to try to pick out solutions that day. Okay, so I'll update that and I'll put it in boldface and stuff. All right, so last time we were talking about problems as undirected graphs. We ended up just talking about one of them. The other two problems are morally very similar, although there's some problem-specific details that vary. But we talked about the independent set problem, trying to take a lot of vertices that aren't neighboring one another. And, we showed a couple things. One was that in a completely general graph, this problem is hard in the sense that a polynomial time algorithm will give you a polynomial time algorithm for SAT. But then we moved on to special cases of graphs. For example, we looked at the problem over intervals. In fact, we looked at the weighted problem over intervals. And we found that with just one slight trick, ordering the intervals by their left endpoint, then in fact you can make this into a good algorithm, a simple algorithm as well. We also looked at the special case of trees. Okay, and I think the key point there's two key points. One was trying to figure out how to look at trees in a way that gives you some kind of, useful decomposition structure, some kind of induction hypothesis. So there the idea was to root the trees so you have a strong notion of subtrees. That was a big step. Another trick that we added was when we're doing this brute force approach, there was a little technical issue of having to do with sort of subproblems being a little bit related to the choice in the previous problem. Because if you took a vertex at the root, you really couldn't include the children in the independent set. And one slick way to do this was to just add an extra flag to your recursive function. You add this and everything becomes much easier. Okay, so it's a nice example of, whatever you're trying to do, if you actually try to do more, it becomes much easier because you have a stronger induction hypothesis to work with. Okay. All right, so today we're going to look at problems in directed graphs. Okay, I got the slight impression from the undergraduate TAs who helped me out that you have seen some of this stuff before, but I'll pretend we haven't. So we'll be looking at graphs, directed graphs without cycles, a certain kind of sorting that can be done with this, discuss this very basic problem of reachability, an algorithm called DFS Search, a notion of strongly connected components. And by the end of this, although at some level directed graphs is a very versatile and loose model, we'll have sort of quite a lot of tools to work with them, especially as concerns problems concerning reachability, whether one vertex can get to another. Okay. Later, we'll look at the related problem of trying to find a way to get from point A to point B as fast as possible. Okay, but today just, can you get there? Okay, so we know what graphs are. Edges can be undirected or directed. Last time they're undirected, this time directed. Okay, and I think you guys have probably been introduced to the sort of implicit in our last discussion, how graphs are represented. One basic way is to have what's called an adjacency list, which is just for each vertex, list all the edges that say leave it, and all those opposite endpoints, and so forth. The main alternative is an adjacency matrix, where you make an n by n two-dimensional array, and you just put a 1 there between u and v if there's an edge between u and v. Okay. All right, that's all it had. All right, so let's talk about what is sort of a very nice special case of directed graphs. Those are ones that have no directed cycles. Okay, so just recall that a cycle just means you can start and end in the same place. Okay, and if you look at the graph I have drawn there, there are no directed cycles. In fact, all the edges are going from your left to your right. Okay, we'll address kind of how to work with cycles a little later. Okay, now in a directed acyclic graph, actually this definition isn't specific to acyclic graphs. A source, sometimes if a vertex has only outgoing vertices and no outgoing edges and no incoming edges, we'll call it a source. And sometimes when a vertex has incoming edges but no outgoing edges, we'll call it a sink. Okay? Things can kind of start at a source, things can end at a sink. Okay. I will suggest that every directed acyclic graph, or DAG, has at least one source and at least one sink. Well, my question to you is why? Sure. Yeah, so somewhere it's going to introduce a cycle. So I'll do it on this picture. Let's pick any vertex. If it's not a source, okay, there's someone going to it, so we'll go backwards. There must be some vertex that came before. If this is not a source, of course, in this picture, it looks, this is, of course, a DAG. So you run into a source. But the reason why this can't go on ad infinitum, right? If eventually you run out of new vertices, if you keep going backwards. And the first time, let's say for the sake of example, that wasn't a source and you can keep going backwards. The first time a vertex repeats, you found a cycle. Okay. So if there's no cycles, you're not going to repeat vertices. The point where it stops must be a source. Okay. The same argument, of course, in the other direction helps you find a sink. Okay. So there are kind of a natural sense of beginning vertices and end vertices. Okay. All right, this seems like a very special and convenient kind of graph. Is it very common? So let me give an example. This is not the last time we'll talk about circuits. I'm only going to focus on how it is an example of a directed acyclic graph today. So a circuit is a lot like a Boolean formula, but it's sort of arranged in a graph. So, you have some inputs. Okay, I'm sorry. Okay. Oh, that's better. Okay. All right. So you have you have inputs. You do some logical operators, and you output some 1 bit. Okay. It's almost self-explanatory, but this could be true or this could be false, and sort of that information gets propagated through this circuit network. Okay. So if this was like true, and this was like false. Okay, the false would go up here. It runs into a not. It becomes a true. It goes up here. It becomes a false. Okay. Now, the true will go this way, and also this true into an OR. So that'll evaluate the true. Likewise, it's getting a little messy. This false will go this way. That false will go that way. That'll come out to false. That is right. Anyway, and it says false and true. That will come out to false. Okay, so I clearly didn't do this right. But nonetheless, you can see it doesn't seem to quite implement XOR, but that's okay. But that's the basic idea, is that just these bits, flow through the network. Okay. The reason why not having circuits is very natural, it's sort of awkward if sort of that those bits of information come back onto itself. There's no natural order of operations when trying to evaluate, these logical things. Okay. You can do a different discussion of trying to operate it, kind of trying to run a circuit over time. But that's way more, complicated besides the point. So I'm kind of thinking this as a static thing, even though we walk through the steps one by one. Okay. All right. So those are logical circuits. Of course, that's very practical. And yeah. So sometimes those nodes are called gates: AND gate, OR gate, NOT gate, input gates. For us, there's always also like a clearly designated output gate. I'm only interested in sort of that last vertex. I probably should have done a better job of highlighting explicitly sort of what is the output bit I'm really interested in. Okay. So that's one natural example of directed acyclic graphs. Okay. So we did just kind of walk through a circuit together, but there's a question of trying to evaluate it using an algorithm. Right? How do I kind of simulate a circuit? So, Jesus, as we did it together, I think the idea was kind of clear. At least if I'm drawing it in this fashion, we sort of worked from bottom up, right? And in particular, the inputs were all kind of sources. And when we did the simulation together, at any point in time, there was sort of a natural next gate to evaluate that sort of had all its inputs prepared. Okay, so sort of in a bottom-up fashion, if I were to draw it, all the edges pointed up, like this. Okay. So at some level, okay, so this has to do with something called, this is not particular to circuits, but there's a natural notion called a topological order. So if I think of each directed edge as noting some kind of precedence, so if A goes to B, that's like saying A is less than equal to B. Okay, which for us in circuits is really saying A needs to be evaluated and have its output ready before I can calculate B. Okay, so for physics, for circuits, this is very natural. Okay, and so a topological ordering is any ordering of vertices. So I'll list V1, V2, V3, V4, V5. That's consistent with the partial order given by the edges. Okay, there may be many topological orderings for a particular DAG. Okay. Okay. So if we wanted to do a topological ordering of this circuit, which I thought implemented addition, but it doesn't matter too much. Okay. What would be a natural candidate for the first vertex, the smallest vertex in this circuit, so to speak? Yeah. Any of the input? Oh, any? It's very exciting. Any of the inputs? Okay, so let's knock it out. So we'll make that's number 1, number 2, number 3, number 4. Okay. What might be a reasonable candidate for fifth? I guess you guys can just shout it. All right, there's 5. How about 6? Okay. 7? This one? Okay. I realize it's a little hard to describe maybe, but just go for it. Yeah, not of 5. That's a good way to describe it. Okay, this and of the 5th one and the 4th one. Halfway done. And of 6 and 7. Six, 9. Oh, sorry. Uh, oh, this one? Okay, sorry, I misheard. All right, there's 11. Okay, I heard 2 people say this one. 12, 9, or. 13, 11, and. 10, 14. Okay. All right, so what were we kind of doing, right? I'm guessing is initially we chose x1 through x4 first because there's no incoming edges. They're all sources, okay? And at some level, we sort of check them off. Imagine removing those edges from the graph, okay? The 5th vertex we chose was a source in the remaining graph. The 6th vertex we chose was a source in the remaining graph. The 7th was also a source. So imagine peeling out these sources one at a time. And what's going on is that you have a DAG. So there's some source. Identify a source. Remove a source. What's left is again a DAG. There must be a source. So you can always remove sources, which for circuits is gates that are like have all their inputs ready to evaluate. Okay. All right. So the nice thing is that if you had computed this topological order and listed the vertices in topological order from left to right, then you can see that all the edges are pointed to the right. Okay. So as far as writing some quick code to evaluate a circuit goes, once you have the topological order, you can just go through the vertices in topological order. I know that by the time I evaluate this node, I've already evaluated any of its inputs. Okay, so it's very useful. Okay. So, and that's really just the algorithm. To compute a topological order, we can always keep removing sources from the graph and listing them. Okay, nothing too profound. All right. I'll only comment for the moment. We'll discuss this in greater detail in upcoming lectures. The fact that we can take a DAG and sort of give some kind of sequential ordering to the vertices, right, suddenly makes it much more amenable to the kind of techniques we use for edit distance and LOTAC and other sequential optimization problems. Once you can give some kind of sensible ordering, that's a lot of structure, and potentially a lot of problems become easier. Okay, so we'll have an upcoming lecture kind of focusing on this distinction. Okay. All right, so if you do some common sense stuff, right? Like, so the algorithm is just removing sources. At some level, you just need to identify vertices within degree 0. So if you maybe go through the graph once at the beginning and you tally up everyone's degrees, and then as you remove sources, you decrease those tallies, then it'll be easy to keep track of which vertices have degree 0 left in the remaining graph. Okay, so it's not so hard to do this whole thing in linear time. It's a little bit funny because we're actually sorting a graph faster than we can sort numbers. That's a little odd. Okay. All right. Okay, so much for acyclic graphs. Okay. Ideally, all our problems would be on acyclic graphs and everything would be much easier. But of course, they are not. Okay. All right. So we're going to start talking about graphs with cycles, and we're going to focus on reachability problems. Okay. So let's see. Okay. So of course, one example of a directed graph is a street map. We're sort of taking a street as like a directed edge, and maybe intersections are like nodes. Okay. And the problem that I face every morning, which is harder when it's snowing, is I guess getting from Lawson to, where are we here? Okay, I guess it's not so hard. And it's easier now that the street is completely empty of cars. But of course, I go out to here, I follow that edge, I follow that edge, I follow that edge. I usually jaywalk a little bit and take a diagonal there. I almost slipped today. Okay. It's like the first time I've walked in snow this year. Okay, so much for that. But of course, it's very natural to start at point A and ask, how do I get to point B? Okay. All right, let me give another example of a graph that I saw online once. I don't know if people have all seen this before. So I guess this is a maze. Okay. You start from this cat. No, you don't start from that cat. You start from this cat, and you try to make it down to that cat. And the rule is that you can kind of go from cat to cat, but you have to alternate between cats facing forwards and cats facing backwards. Okay, so like you can start here and you can go there. You can go there, right? Forwards, backwards, forwards. I guess eyes indicate forwards. Doesn't make tons of sense, but that's good. All right, you can go there. I'll give you guys like 30 seconds for fun. Anyone find a way to get to the bottom? You can, I guess you can keep going down. Like here's something, you can go like this. Okay, but now I appear to be stuck. Okay, you can try doing stuff like this. Okay, so I won't spoil it for those who haven't solved it. Okay. All right, it'll be in the notes. The only part of the notes you guys will find interesting. All right. Okay. So that's a reachability problem. Okay. In general, give you a directed graph, and I pick out a vertex S. S is supposed to be in the top left corner here, and I ask, can S reach all the other vertices? Okay. I'm going to take a vote, as always. Okay. So, can S reach all the other vertices? Who's not going to vote? Okay, 2 honest souls. Okay, who thinks that S can reach all the other vertices? No one? Okay, all right. Who doesn't think S can reach all the other vertices? Okay. All right. Okay, so you guys are all correct except for 2 people. So there is a triangle sitting in the middle of this graph that actually has no incoming edges. Okay, all right. Hopefully, even though you guys all solved it, all but 2, it still suggests that, this is only like 10 nodes or something, and hopefully it took you more than half of a second to figure out the answer. Okay, it's not that easy. Okay, now imagine doing this, when you're designing a computer chip, right? Then you just have billions of nodes and edges. Imagine doing this when you're mapping the World Wide Web. You have billions of nodes and edges. Okay, so there is a need for a good algorithm for this basic question. Okay, so that's our next task. Okay, and then one point of view I want to make, this is sort of like solving a maze or solving a map problem. But one thing to keep in mind is that sort of the view of the world that the computer sees, the algorithm sees, is not sort of this convenient bird's eye view, but the algorithm is going to kind of be going from node to node, right? It's going to be more like trying to figure out how to use the map using only Google Street View or whatever. Same analogy, rather than getting this kind of maze on your placemat at TGI Fridays or whatever. It's more like being in the maze, right? As far as the data is going to be big, you don't really have a global perspective, or it takes some unit of time to check each subsequent part of the graph. Just one thing to keep in mind. Okay. All right. So, the generic version might be give you a graph, give you 2 vertices, ask if point A can reach point B. Okay. And here might be a natural recursive approach. Okay. So recursively, I want to figure out if point S can reach point T. If S is equal to T, then of course, yes, I can. Otherwise, I'm at S, and I can try visiting all the other vertices V and recursing there. See if V can get to T. Okay. And then if any of them return true, then yes, I can do it. If none of them return true, then no, I can't do it. Okay, this algorithm is kind of obviously correct in the sense that if it terminates and returns true or false, it will indeed be correct. Okay. But there is an issue with this algorithm. Can anyone spot the bug? Yeah.
It can't handle cycles properly because there's no caching mechanism. So if you've got an instance where, say, the first edge of node 1 goes to node 2, and then the first edge of node 2 goes to node 1, that'll just infinitely reverse.
Exactly. So, a simple graph like this, okay? Let me bring this up. If I look at a simple graph like this, and I start at S, the recursive search is just going to go around in circles forever. Okay? Because it has no memory. It's just doing recursive calls. It doesn't realize that it's revisiting the same vertex. Okay? All right, so that's sort of, when we use recursion, it only really works if we have some implicit induction hypothesis. Okay, somehow things are getting smaller. We're not repeating ourselves. That's how I avoid infinite loops. And when there's cycles in a graph for this problem, there's kind of no natural base case. You never stop. Okay, so that's one thing that sort of cycles conceptually represent, is they're going to make it a little bit more challenging to figure out how to break down problems as compared to how we've been doing things for the past few weeks. Okay. All right. So, all right, what's sort of an idea from Hansel and Gretel, or caching was a word. Another way to think of it is leaving breadcrumbs to try to keep track of where you've been, right? At some level, it's much easier to solve a maze if you have a pen than if you just stared at it, at least if it was a harder maze than this one. Or maybe pencil so you can erase. Okay. All right, so that brings us to depth-first search. The only difference between depth-first search and our first recursive algorithm is that we're going to mark vertices when we visit them. Okay. So if a vertex, whenever I call DFS a V, DFS for depth-first search, I'll first check to see if V is marked, meaning I've already visited. If I haven't, the first thing I do is mark it, because now I'm here. Okay. Then I'll explore the edges. Okay, simple enough. But once a vertex is marked, I'm going to exit right away. So I'm already killing off all the infinite loops. Never really visit the same vertex twice. Okay. All right. So if I ran depth-first search from S, maybe we start here, and then maybe the algorithm would go over here, down here. So I should check things off as I visit them. Maybe it'll go here, check that off. This has no outgoing edges, so it's going to kind of back out of the recursive call. It'll keep searching. Mark this vertex because I visited it. Okay. There's no more outgoing edges, so I'll backtrack. Right? Then maybe I'll explore this. Okay. Maybe I'll explore this. Maybe I would explore this. Okay. Kind of gradually making progress. Okay, no more outgoing edges, so we backtrack. Any outgoing? Doesn't look like it. Backtrack. It's getting messy. Backtrack. S has been checked off, but we're not done with this. All that happened within the DFS of S. They were all subcalls. So DFS of S is still kind of on the stack. Now it's back on top of the stack. And we continue. Maybe we go here. And we go here. But this is already checked off, so we kind of backtrack right away. Didn't put a check there, though. We backtrack. Okay. We're almost done. I'll go here. We mark it. Maybe I'll search here. That's already checked, so I exit right away. I go here. That's already there. That's already there. Okay, now I'm back in that root call at DFS of S, but I've already gone through all of its edges. Okay, and now I'm done. And then you'll see that triangle in the middle, we never touched. Of course, we couldn't get to it. But maybe more interestingly, everything else was marked. We did search everything that could be reached. Okay, and the algorithm terminated, even if halfway through it started to get awfully boring. Okay. But it's mechanical, it's methodical, it works. Ultimately, it's linear time because I only actually traverse each edge once. Okay, so that's the algorithm. two claims. I guess one is that it runs in linear time. That's sort of easy to address. I only traverse an edge right after I mark the vertex, right? Once I mark it, that's the only time I go across an edge VW. We only mark each vertex once, so I only go across each edge once. Okay. More interesting, although maybe not so surprising having gone through an example, is proving that it does visit all the vertices. Okay. So let's do that. I want to prove that when I call DFS of V, I will visit and mark and search all the vertices that are reachable from V. There is a path from V to that vertex. DFS will find it. Okay, so we're going to set this up as a short proof by contradiction. You run DFS from V, some vertices get visited, some vertices don't. Okay. So I'll say A are the vertices that get marked, that get visited. B are the remaining vertices. Okay. And then suppose by contradiction, there is some vertex W that is reachable from V, but for some reason didn't get marked. So it's sitting in that set B. Okay. All right, so if it's reachable, there's some path getting from A to B, or V to W, right? Whatever the path is. And at some point, you start in one color, you end in the other color. I must cross over at some point. Here I've crossed over several times. Okay. So there must be a first vertex, A, that's sort of in capital A, that crosses over along an edge to B, right? So we know the path crosses over. Look at the first time it crosses over. Let A be on the marked side, B on the unmarked side. Okay. Now, as soon as I marked A, right, we put a check mark, we should have triggered, so this would be A, we should have started a loop that goes through all the edges leaving A. Okay. So at some point, one of these edges should have been AB, right? That path has that edge AB. We know AB exists from that path. Okay, so that's impossible. Once A is marked, it's going to search all the edges as well. That would contradict this setup. Okay, whatever. That's a proof. Maybe only confirms common sense. Okay. And again, I guess for the sake of completion, the linear time is just coming from marking. I only explore an edge VW after marking V. V only gets marked once. So this should be U. U to V only gets searched after marking U. Each vertex only gets marked once. So I only traverse each edge once. Okay, no big deal. Okay, so that's it. Depth first search. Very practical, very simple. I'm guessing you might have seen this before in some class. Okay. All right. It takes linear time. It's going to visit everyone reachable from V. It's very nice. Okay. All right. So just one additional comment. It's often the case that I sort of want to loop through and do something to every vertex in the graph. That's very common. But maybe the graph is given to you as like an adjacency list kind of representation or something like that. But in any case, if I call DFS from V, I'll only visit the vertices reachable from V. Sometimes it's desirable to make sure you reach everyone anyway. So the simple idea is to wrap the whole thing in a loop. Okay, it's called DFS from V from every V. When vertices are already marked, you just skip it, so you won't waste any time. Okay, but there's a lot of situations that call for this. One is coming up. Okay. Of course, this general idea of a driver is not at all particular to DFS. Okay. All right, so before moving on, I want to talk a little bit about this reachability problem, which I'm sure we all take for granted. But the key idea, really the reason why it works is because of the marking, because of the breadcrumbs. And so there's this very interesting theoretical question. Can you do anything without memory, without breadcrumbs? Okay. So suppose I only gave you log n memory times a constant. So that's basically enough memory to maybe remember the ID of a few vertices. Like you're walking on a graph, you can remember what vertex you're on. It's enough memory for a counter, right? Because I can count to n with log n bits. It's not enough memory to mark every single vertex. I need n memory for that. Okay, so it's a very nice and interesting question. And I guess what makes it interesting is that we have some answers to this, as basic as it is. Okay. Yeah.
Maybe just for each loop, remember where you started, only so that you will only go back when you reach that vertex again, so that you don't remember every vertex.
Well, okay. So the question was maybe just remember where you started, and then otherwise basically call recursive search. But of course, you can go like this, and you'll get screwed.
If you go to the second one, then the point of where you started becomes the second one.
So it's very hard to remember where okay. So it could be a long path to a loop. You don't know when the loop starts without marking everything on the path and stuff like that. It's quite tricky. Okay. So let me briefly go over what you can do. How to prove it is a different matter. Okay. If you're allowed to use randomization, this is an amazing algorithm. If you're allowed to use randomization, then a random walk will work. So I want to find out if I can get from S to T. I start at S, I pick a random neighbor, and I just go there. Now I'm at U. At U, I pick a random neighbor, and I go there. This is only for undirected graphs. Okay? And you do this for a while, for a polynomial number of steps. You can show that after about m times n steps, m is the number of edges, n is the number of vertices, if S can reach T, with constant probability, you'll have reached T. Okay? It's not easy to prove. In fact, there's a very interesting connection to electrical networks to prove it. It's sort of proven by to some extent, a physical metaphor. Okay. So with constant probability, you can figure it out. To make that probability of success go up, just run this experiment 100 times. The odds of all 100 times failing, if the odds of succeeding are, say, 1/2, is 1/2 to the 100. Right? So it's not a deterministic algorithm, but you can make that probability error plummet by just repeating independent trials. It's a very nice idea. Okay. All right, how about deterministically? You can't take a random walk. I'll take a very quick vote. No time for abstaining people. Who thinks we can do this deterministically? Okay. I'll say that's like 20%. And who doesn't think we can do it deterministically? Okay, pretty close to remaining. Because it's clear where randomization is helpful, although I didn't prove anything to you. Okay. Amazingly, the answer is yes. Okay. And it was only answered fairly recently given how basic this problem is. 2008. Okay. It turns out you can take the randomized algorithms approach, the randomized walk approach, and you can actually de-randomize it. Okay. What does that mean? You know, we don't, there's some technical details, but it's one of the things we talk about in the randomized algorithms course. But it's unbelievable. Okay. What about directed graphs? That was only for undirected graphs. Okay. Who thinks that we have an algorithm for directed graphs? Okay. A little bit less, I'll say 15%. And who doesn't? A little bit less, maybe 70%. Okay. So this, not only do we not have an algorithm, but we don't even know the answer. We can't prove that we don't have an algorithm. Okay. However, there is this very nice thing from 1970 that says that if you use log square n space and you use more than polynomial time, this is actually less than exponential, but more than polynomial, so it's sub-exponential time, sometimes they say, then you can actually do it. Okay, so we're stuck with this sort of in-between answer. It's sort of hard to believe that's the best algorithm. But anyway. Okay, so these are some of the big questions out there. Okay, back to planet Earth. Okay. All right, let me talk about. So we talked a little bit at the beginning about topological order and just removing sources to list of vertices from left to right. Okay. So let me briefly mention the opposite. I mean, you can do something with depth first search as well. And what it does is sort of gives you some information about the order in which depth first search is visiting these vertices. Okay. So suppose I call depth first search on a particular vertex V. Between the time that that vertex is marked, right? So I visit it and I mark it, and that call, the depth first search, exits. Okay, so I'm only looking inside here. Then I'm only going to visit vertices that can reach V. Okay, I'll take that as a fact. Okay. All right, so what does that fact imply? Okay. Suppose I have two vertices, okay, where V can reach W, but W cannot reach V. Okay. Then any depth first search that visits V and W will always kind of finish searching W before finishing searching V. That's the claim. Okay. So what's the idea? Okay. I have two cases. One case is that DFS will mark V first. The other case is it marks W first. Again, V can reach W, W cannot reach V. Okay. And I think there's not much to say here. You know, if suppose I mark V, our depth first search is going to exhaustively search everyone that V can reach before it finishes DFS V. So I think there's nothing actually really to say. Visits W before finishing DFS V. Okay, so that's one case. The other case is when W gets marked first. Okay, so if depth first search visits W first, it hasn't visited V yet. We just said that we're only going to visit the vertices that are reachable from W before exiting that call to DFSW. But in particular, we won't visit V. Okay. All right, maybe that's too straightforward to call it a real proof, but a real lemma. Okay, so What does that imply? So every time V can reach W, but W cannot reach V, I know that I'm going to finish searching W before finishing searching V. That's sort of one rule we have. Now, what are the implications? Suppose I print out those vertices as I exit the calls to DFSV. So let's look at the order in which the calls finish. Okay, so imagine I augment my code with this last extra line. So this is, again, only if it's searching for the first time. So it's underneath the if statement. But on the way out, I'm printing out the name of the vertex, or appending it to the output somehow. Okay, now we're interested in what can we say about this ordering. This is called a post DFS ordering, because it happens at the end. Okay. All right. So suppose the graph is a DAG, right? If a vertex U can reach a vertex V, then I'll suggest that V cannot reach U, but why? Yeah. Yeah, that would give you a cycle. Okay. So every time U can reach V, that automatically means V is printed before U. And as a result, so that means, okay, so if there's in particular, if there's an edge from U to V, then V is printed before U. Okay. So if I actually print out all these vertices, all the edges have to go to the left in a DAG. Okay. So the post DFS order will actually give you a reverse topological ordering. Okay. It seems sort of a silly way to do it compared to removing sources. That seems more straightforward. But nonetheless, it gives us a second algorithm for computing a topological ordering. Okay. All right, so now here comes our last section. And I think we have a good amount of time. So now, before we were interested in this sort of reachability question, which is posed a little asymmetrically. Can S reach T? Okay. Now we're going to move on to thinking about situations when S can reach T and T can reach S, or maybe not. Okay. So we say that two vertices are strongly connected. Okay. If S can reach T and T can reach S, which of course can happen. Okay. Just as far as vocabulary goes, a graph is called strongly connected if every pair is strongly connected. Like you're kind of hoping that the real world maps are strongly connected. Otherwise, you can get stuck in a ditch and never get out. All right. Good. All right. So the claim, as far as kind of strong connectivity goes, the point I want to make here is that there's a lot of symmetry imposed by this definition. The fancy word is to say that it defines an equivalence class. If A is strongly connected to B, and B is strongly connected to C, then C is strongly connected to A. If A is strongly connected to B, B is strongly connected to A. Okay, as far as connectivity goes, they're equivalent. Okay. And there's not much to say or to prove. I just want to show that if U is strongly connected to V and V is strongly connected to W, then U and W are strongly connected as well. Okay. But of course, if I have paths like this, I can always combine them. That gives you some walk from U to W. And vice versa, we get a single walk from W to U. It's possible that vertices repeat if those paths are crossing, but that doesn't appear in the picture. Okay, fine. So there's some transitivity going on, of course. So what does that, imply? Okay, so Now here comes maybe the most interesting definition left. So so there's this kind of strong symmetry between strongly connected vertices. So we can refer to, a set of vertices where everyone's strongly connected with each other. Okay, once you have an equivalence class, you can now partition whatever objects you're working with by equivalence class. What strongly connected component is the name of an equivalence class. Okay. So for example, we have this triangle here where everyone is strongly connected amongst themselves, okay, but not strongly connected with anyone else. Okay. This vertex by itself is its own equivalence class because it can't reach anyone. Okay. Another equivalence class would be this sync vertex down below. Again, it can't reach anyone, so its own strongly connected component. Okay, anyone want to suggest any other strongly connected components? So previously we had a triangle in the middle where otherwise no one could reach it. So that would give another kind of strongly connected component. Okay. All right. Now I know that here's a triangle. Oh no, that's not a triangle. All right, suppose I cheat because some of the examples later are messed up. All right, if I redrew that edge like that, I know that these three vertices are strongly connected with each other. Okay. Oh, I have a couple of arrows off. I must have miscopied. Okay. All right, forget this. Anyway, if I rearranged the arrows and cheated, I made a little mistake in my preparation. There will be another directed cycles like that. Okay, and consequently, all of these would form one strongly connected component. Okay, so if I had my arrows correctly initially, okay, it would have colored naturally like this. So in every color class, all the vertices can reach each other. And across color classes, maybe A can reach B, but B then cannot reach A. Okay. So we can always break down a directed graph into its strongly connected components. Okay. All right, SCC for short. Okay, so now we want to figure out how to do this task algorithmically. It seems useful to sort of know which vertices are kind of very closely related in this connectivity sense and which ones aren't. Okay. And so the first task, instead of worrying about all the strongly connected components, is just try to do one at a time. Okay, so let's do that. Suppose I have a vertex V in the top left, and I want to find a strongly connected component of V. Okay, so I want to find all the vertices that V can reach and can also reach V. I think an obvious first step is to run DFS from V and figure out at least who V can reach. All right, so that's step one. Now my question to you is, what would be step two? How can I figure out all the vertices that can reach V? Yeah.
Maybe
Sure. We could then run DFS from all W, other vertices besides V, right? And see which of them can reach V. Okay? The total running time would be, I run DFS from every vertex, so we get something like M times N time. Okay? Can we do better? Yeah. Okay, so I can run it from, let's say this was the tree. I can run it from here, in the sense that if W can get back to V, I'll kind of have this cycle that proves that they're in the same strongly connected component, right? And I can kind of look at all the leaves, so to speak, of sort of that tree, that search tree carved out by depth first search. That said, there could still be a lot of leaves. In the worst case, I might still be running DFS from maybe not all N, but N over 10 nodes. So it doesn't necessarily improve my running time in the worst case. Yeah.
As you run DFS from V, if you find breadcrumbs, that might hint at turning around or cycling back.
All right, so at a high level, can we maybe open up the depth first search algorithm, try to do something clever? First of all, as I'm searching along here, I don't know, maybe I find some backwards edges. Should I maybe try to incorporate that information? Okay. I'll suggest that this is going to be complicated. I think that's fair. It's not impossible, I guess. I'm looking for a conceptually trickier but easier way to identify all the vertices that can reach V. That'll be much faster and won't require new algorithms. Okay. So let me give a big hint. Okay. So this class is called algorithms, but sometimes the secret to the class is we rarely make a new algorithm. We think about how to use the algorithm. Okay. So the hint is don't change the algorithm. Change the graph. Okay. My goal is to find all the vertices that can reach V. An idea was to change DFS, and I'm saying don't change DFS, change how you use it. Yeah. We can reverse all the edges in the graph, right? So if W can reach V, then V can reach W in the reverse graph. So I can reverse all the edges and then run DFS from V, just once. Okay? And moreover, I don't have to prove anything. I'm not inventing a new algorithm. Yeah.
Wait, you said run DFS from V just once?
That's right. So that's right. So let's reverse the graph. Let's call the graph G sub R, R for reverse. Okay. We'll run DFS from V, but we'll use the reversed edges. So we rebuild the graph. So we spend linear time to rebuild the graph, but who cares? DFS is going to take linear time. Okay. And then we'll return, all the vertices that appeared in both. Okay. So we reverse the graph and then we run DFS, and that'll identify all the vertices that can reach V. Okay. Nice idea. It's obviously much faster because now I only need one depth first search in that second stage. So we end up running two depth first search, and I rebuild the graph. The whole thing's linear time. Okay. And of course, this lesson of changing the graph is more general. Okay, good. All right, so maybe a natural approach then to trying to identify, yeah, okay, this is not so interesting. All right, so that's one strongly connected component from a vertex V. Okay, so how might we get all the strongly connected components? I guess maybe the most natural idea is to for one vertex at a time identify its strongly connected component. Okay. And so I'll pay n times m plus n, and I'll get this quadratic running time. M is probably bigger than n. Okay. All right, so that's reasonable. Now we know it's probably not as hard as SAT or something because we can do it in polynomial time. But the question is, can we do better? Okay. Question is, can we do better? All right. Let's see what's next. All right, so look at the strongly connected components of this graph, right? Highlighted by color. Okay. Now, suppose I sort of like, imagine taking each of the connected components and shrinking it to a vertex, like a sort of a mega vertex. So let me give an example. Okay. So I'll take this and I'll shrink it. Okay, and I want to take I'll take this vertex by itself, this vertex by itself. So I want to think of each strongly connected component as a vertex. So I want to take all the vertices and contract it and then sort of take the glue of the edges that remain. It's a little bit hard to rip out this triangle. Sorry. So I'll take this out. I should have taken it all the way out. Okay, I'm making a big mess. Okay. I want to think of this as a single vertex. So I'll shrink that. And lastly, I have this one. I want to think of this as a single vertex, please. It's less impressive when it takes me like 10 minutes. Okay, I have a picture down here. But now that's in the way. Okay, let's look down here. Okay. Once I've compressed every strongly connected component, once I've compressed every strongly connected component to a single vertex like this, and I've sort of retained the edges. So if there was an edge from some yellow vertex to some purple vertex, now I just have a vertex from the yellow conglomerate to the purple conglomerate. Okay. But the nice thing is that because I'm contracting strongly connected components, there's no cycles left in this contracted graph. If there was a cycle, if I could have gone from yellow to purple to green, back to yellow, that cycle would put all of them in the same strongly connected component. Okay. So once I contract all the strongly connected components, what's left is a DAG. Okay, so sometimes it's called the DAG of strongly connected components. Okay. We've gotten rid of the cycles. Okay. So now the current approach we're looking at was just to pick any arbitrary vertex and grab the strongly connected component. Okay. And whatever, it works, but we're trying to do better. And so what I would like to do is maybe I can bring a picture with me. No time to bring a picture, oh well. Okay, so now what I wanted to think about is, suppose I could sort of pick out which vertex I wanted to search from first. Okay, it would be very nice if somehow I could have, say, picked this one first. Okay, why? Because when I start searching from this vertex to find a strongly connected component, I'll never leave that vertex because it's in the sync component. Okay, it never leaves. Okay, so it'll be really great if I could sort of do something like a topological sort, where I'm always able to pluck a vertex out of the sync component. We don't know how yet, but for the sake of discussion. Okay, because if I did that, and then I could eliminate this vertex, right? So first of all, if I had picked a vertex in a sync component, to obtain the strongly connected component, I would only have to run DFS once from that vertex. Anyone it can reach it because it's in the sync component. You don't know it's in the sync component, but let's pretend. Okay. So one thing is that, so if I change my algorithm, so that I'm not just picking any vertex among those remaining, but in particular one from a sync component, I only have to run DFS instead of in the reverse graph as well. Okay. And once I remove this from the graph, I rip it out. Okay, we can identify another one from a sync component. Run depth first search once. What would be a sync component here? The green. So maybe I run it from here. No, that is no, that's a source component. Sorry. At this point, the purple is a sync component. There's no vertices leaving purple. So maybe I run depth first search from here. I rip out that strongly connected component. Now the yellow is a sync component. I rip it out. And finally, all that's left is one last component by itself. I run depth first search once, and I rip it out of the graph. You know, it'd be nice if I can peel out the sync components because I only need to run depth first search once. Moreover, each of those depth first search never leaves its own component, which means altogether I've only looked at each edge once. That whole process would take linear time. Okay, so all that's left is the punchline, which is how to do this on the fly if you didn't know the sync components. Okay, so let me just explain it and I'll skip the proof. Okay. All right, so I want to identify the sync components, and what we're going to use is DFS again. It's very clever. Okay. Now, remember we had this, we had no time, but remember we had post-order DFS traversal, okay, which had some relationship to topological order. Now, you might think that the first vertex has to be a sync, like DFS gets to the bottom and then it propagates back up. That's actually not quite true, okay? But you can prove that the last vertex in the post-DFS order is always a source, okay? You have to make sure you put a driver around the whole thing, okay? So DFS will always give you access to a vertex and a source component, but I want a vertex and a sync component. This is our last question, real question. If I can always get a vertex and a source component, how can I use that to get a vertex and a sync component? Yeah. Reverse the graph. If I reverse the graph and compute the post-DFS order, the last vertex will be in a sync component. Okay? And I can use, hopefully it's Anna. Let's go to the prepared version. No, that was a bad idea. Okay. So the only difference is we're going to run post-DFS on the reverse graph first, and I'm going to pick out those vertices in order of that post-DFS on the reverse graph. That first vertex is going to be in a sync component. I do DFS, rip it out. The next vertex left, that again will be in a sync component remaining. Okay, just by thinking about what post-DFS is doing, run DFS, rip it out. So by running DFS on the reverse graph, we can actually pull out all the strongly connected components by always searching from a sync component. It's very clever. And then the notes will give the full proof in detail. Okay? You can do the whole thing in linear time. That's incredibly useful. All right, thank you.